Okay, so we had some work done there with JUnit and BlueJ. So just by way of review, JUnit is a Java test framework. You create test cases, which are methods that actually do the work of creating objects and then invoking methods on those objects and then testing assertions about the results. The test classes are the um, Java classes that are JUnit classes that contain the test methods. The assertions are used to um, verify that what comes back from the method is what you're expecting. The one thing that we didn't build out, but that hopefully you did get to build out in your examples, is the notion of a fixture. A fixture, you may have noticed in the test classes that as you started the class, you would create objects, and then they would have to be made, and if you were testing the same objects over and over and over again, they would be created in each class. If you establish a fixture, what happens is that those get set up before each test, and they get torn down at the end of each test, but they don't have to be created inside of each individual test case. So by setting up a JUnit fixture, you can create a set of objects that get used repeatedly so that you don't accidentally change values from one test to the next. So just keep that in mind, and you can use that to your advantage in future projects. Let's shift gears away from testing and move over to debugging. So just as a callback to previous lectures in this week, remember that what we are interested in now is detecting the bug and finding the source of these bugs. So there are some techniques, some of which you've already begun adopting and some of which are a little bit newer to you that we can work with to figure out what is happening inside of your code. Something that is fairly popular with, I would say, forward-thinking programming departments is the notion of a manual walkthrough. This is a process by which a subset or the entire coding team will sit down in a conference room while the code is being projected, and everyone is kind of verifying that it does what it's supposed to do. This is something that can be done as part of an extreme programming methodology. It's good to develop the discipline to be able to do a manual walkthrough and to actually trace down and note the proper sequence of steps that the code is executing. It requires you to slow yourself down, to think like the computer and really see what's being told in the code, and so and how the state of the objects change from method calls, and then throwing in print statements, and then also using interactive debuggers. Now, something we want to keep in mind is that properly designed large-scale projects are modularized, and that is like one programming team could be working on a module, a different programming team could work on a different module, and they have to pass information back and forth through a code interface. Part of what makes dividing large tasks up possible is the notion of being able to establish a standard by which information will be passed. Setting up a code interface allows teams to work on modules individually and allows those teams to also test with expected values. And then those pieces can be stitched together and then tested as a larger unit. And so that part of testing is called integration testing. And that is another part of large-scale software development. The book uses the example of a calculator. There's a class that's responsible for handling the logic of the arithmetic, and then there's another module that is responsible for handling the gathering of input from the end user. In the sample project, there are two versions, one that allows you to enter information through a BlueJ, through an object that you create in BlueJ, and then call the methods individually. And then there's a more complex interface, which is actually a GUI, that then ties back into the same calculator engine. But this separation of concerns is something that is practiced regularly in software development. If we consider the calculator engine project, one way to understand what that object can do is to not look at the body of the methods, but just at the method headers. So getDisplayValue takes no parameters, returns an integer. NumberPressed takes an integer and returns no value. The plus operator is in effect, when the plus button is pressed, it indicates that we are going to add the next value. Minus operator, we just indicate that that is the minus button being pressed. The equals method completes the calculation based on the internal state of the object, and the clear method resets the calculator equivalent to hitting the C button to reset it to be able to do its next piece of calculation. The thing is, the calculator engine project, as it's written, doesn't perform as advertised. So part of what we're going to do in this part of the chapter is to spend a little time poking at that calculator engine and seeing if there is a way for us to improve upon it. Now, one of the ways that you can look at the calculator engine is to do a manual walkthrough. It's low tech, but it is where you keep a sheet of paper, or if you're doing it with a group, a whiteboard, and you go through and you record the internal state of the objects on each line of code. And generally speaking, what you do is you don't change the values on the whiteboard or cross out. You just make a growing list of a grid of, on this step, these variables have these values in it, and you just update everything as you go so that you know what's happening in the object as each line is executed. This can be extremely powerful for finding bugs. One of the reasons we use BlueJ in this course is that it gives us the ability to peek into the object and see the object's state. Generally speaking, in Java, in object-oriented languages, bugs will come up when you're trying to do things and you are assuming certain things about what's happening inside the object, and the object is in a different state than your code expects. So being able to trace through and know that what you thought was the object state is not what the object state actually is can be incredibly powerful and highlight where these bugs are coming from. So If we go through a debugger would be showing us the state sort of step by step, but showing us the changes dynamically. If we're doing it by hand, we can actually maintain a historical list as we go through until we leave the method. Another thing that can be useful is sort of used in pair programming, similar to a manual walkthrough where one person is talking through the code to another person. Pair programming is a subset of the notion of extreme programming, and this is an idea, I believe it came out in the 90s or early 2000s, that you can be more effective as a programmer programming with someone else. And if you just think about how many times you've shown your code to a colleague, a peer, a classmate, and something that you've been banging your head against because you've just been skipping right over some areas, they look at your code and say, oh, wait a second, this variable's initialized with the wrong value. Or this branch of the if statement will never be taken. Or when you try to explain it to someone, how many times have you started to say, well, it does this, it does this. Oh, wait, I see what the problem is. You know, slowing down, getting away from the computer, doing some verbal walkthroughs can be incredibly powerful. While we're talking about it in a very informal sense, there are processes in the software engineering literature about how formal walkthroughs and code inspections can be performed. Another way to do debugging is the one that you were probably introduced to in CSIT 103 or 105, which is throwing in some system out printlns. Doesn't require any special tools. Every programming language can do it. You want to make sure that you are documenting the proper area of code. And ideally, you want to set up a structure where you can specify that some messages can be turned off and other messages can be turned on. And that in itself can lead to potential errors if you're adding in additional logic. And then stripping that code back out is challenging because you want to make sure that the debug code doesn't make it into your shipping build, because it could potentially slow down or impact the running of the software. Okay, testing, debugging. The important thing to know is that you have options. It's not a one-size-fits-all. Some things are going to require human testing. Some things are tests that can be automated. Some debugging might be best done in an interactive debugger. Other debugging must be done in a conference room with the code projected. The thing to keep in mind is that you have many different options on your tool belt to apply here. Just like a master carpenter will have different saws or different screwdrivers or different chisels for different purposes. I do recommend that you automate whenever possible. People get tired, they get fatigued, and when they get fatigued, they run shortcuts or they get sloppy. So if it's something that we've already done the tests, record those tests and have the computer do those for regression testing. It reduces human error. It also means that it's more likely that the test will be run. When we deal with debuggers, debuggers tend to be language specific, IDE specific. You want to understand how these tools work. You've probably gotten comfortable with setting breakpoints and using step and step into, and setting future breakpoints and just continuing until the next block of code. One thing you should keep in your observation is that debuggers will also show you the sequence of calls that have been made. This is called your stack trace. And so you can see which method called which method, which called which method, which called which method to get you into the one that you're currently looking at. And debuggers will also do a good job at showing the current local variables, as well as the object state. Okay, all of these things are important, and there's one topic that's not mentioned in your textbook that I want to bring in as well. With all of this additional information, you may be tempted to try to optimize your code, which is different than fixing bugs. But as you're going through your time here learning to become more effective programmers, you might say, well, this code will run faster if I do this. And I want to introduce to you the notion of a profiler. There have been decades of research on how to write more efficient code, and that code has been rolled into the output of compilers. That is to say, your attempt at optimizing code in source code is not going to be as effective as what the compiler can do when it gets translated down to machine code, or in Java's case, to byte code. So, what you may be tempted to do as you are writing your source code, you might say, well, if I eliminate this line and combine a couple of comparisons into one statement, this will run faster. But you don't know that, because the computer runs so fast you can't see how fast it's running. What a profiler does is it gets attached to your running program, and it tells you exactly how long each method call is taking. If performance is important, you do not modify your code on the basis of source. You have to measure it as it's running, and then determine where your slowdowns are, and then make the changes there. So here's an example from a screen grab from a Java profiler, and it's just giving us feedback on how much time is being spent in different method calls. So if we were to focus on one of these methods to optimize, it wouldn't be as important as focusing on this method, which is taking almost a full second inside of it. This is, I'm sorry, invocations. It's being called 1,000 times. Let me rephrase that. Maybe if we were working here, these calls are taking less time, whereas a call out here, like this call, which takes over 10 seconds, this is where we need to be spending our time. I'm sorry. See, the thing is, I'm looking at this Java profiler, but the reason I threw this in is really for the game developers dealing with profilers inside of the Unity game engine. There we're concerned about things like how much CPU are we using, how much GPU are we using on the render thread, how much memory are we using, how much network bandwidth are we using, how many draw calls are being sent to the GPU. And so this tool has a profiler built into it, as opposed to Java, which we would need to get a third-party tool and wire it in, and we will not be doing in this course. But just keep in mind that profilers are where you need to start if you're concerned about performance, not about debugging. Chapter 9 ends with just a callback to Chapter 5, which is the chapter we skipped, and we'll be returning to. But just know that the Lambda operations are more challenging to debug, and so this peak statement is what allows you to throw in some print statements to see what's happening in stream processing. So again, this new feature, a little bit harder to use, and requires a different approach, which is why we're not embracing it until we get to GUIs. So let's wrap this up. No program's going to be error-free. It's a fact of life. You're going to have to debug. you're going to have to test. The best we can hope for is to set up a situation where the bugs are easy to find. Debugging can seem very frustrating, especially as you're starting off, because you don't have an internal library, mental library of what these results can be caused by. And so it makes it hard to trace things down. I will say it never really gets better, because what will happen is the bugs that you know how to solve, you'll either prevent in your initial code, or when you see them, they will become trivial to fix. But you will always find newer, more challenging bugs in your software if you're doing anything interesting. And you're all going to be doing things that are interesting. And so you're all going to have annoying bugs in your future. But towards that end, write your code modularly, set up tests, automate that testing, make sure that you regression test, and give yourself multiple ways to deal with debugging. Embrace the debugger for the different IDEs that you have. Still use print statements when they're necessary. Sit down with a colleague and talk through your code. Share a screen and have someone else look at your code. Sometimes it's just fatigue that's preventing you from seeing it. And sometimes it's like, oh man, we need to bring in our project lead because there's no way, or our tech lead because I don't see what's happening here. And that's also part of the game. Okay. Hopefully this gave you some things to think about, and I'll see you next week for Chapter 10 and 11.